welcome to the third and the last lecture of this week. Well, this lecture is going to be also the last lecture of EE501, so we're going to finalize all of the topics today. So remember what we did in the last lecture. We have actually seen the concept of functions of a matrix, and we defined it, and we defined what it wasn't, and we defined what it was. And then we have seen the first method of calculation of f of a. Well, in this last lecture, we are going to see the second method of calculation of f of a. But first, let me remind you what we have done so far. So here we define this scalar function f of s. Okay, and we think about it as Taylor series expansion. So this Taylor series expansion looks like this. So I have I from 0 to infinity, f to the ith order derivative evaluated at s0 divided by I factorial, s minus s0 to the power I. Okay? So remember, when we actually want to simplify this, we simply choose s0 equals to 0. Okay? That gives me f of s is equal to I from 0 to infinity, fi evaluated at 0 divided by I factorial, s to the power I. And remember, in the last lecture, I have defined this alpha I coefficients as fi evaluated at 0 divided by I factorial. Then this turned into the I from 0 to infinity, alpha I s to the I. Okay? So we are given this expansion, and then we would like to find f of a, and we are using these expansions in order to define f of a. So remember, I can define f of a as follows. I can substitute s equals to a in this series. So I have I from 0 to infinity, fi evaluated at s0. These are just scalars here. So the ith order derivative of f evaluated at s0 divided by I factorial is just a scalar. And here s is going to be substituted with a, and this s0 is going to turn into s0 times the identity matrix. So I have I factorial, and I would have a minus s0 identity to the power I. This is my f of a, and in the last lecture I had instead used this Taylor series expansion in order to be able to define f of a, and it gave me the following representation. I from 0 to infinity, alpha I, and I have a to the I here. And if both of these Taylor series expansions are convergent, then we can be sure that these two definitions are the same. Okay? So what did we do last time? So remember, we started with f of a, which is given as this definition, a to the I, and then I have written this as a finite, as a polynomial here. So I reduced the number of terms in this infinite summation into finite number of terms. How did I do it? We did it using the Cayley-Hamilton theorem, or the equivalent of Cayley-Hamilton theorem applied to the minimal polynomial. Okay? In that case, this turned into a polynomial C0i plus C1a going until Cl minus 1 a to the L minus 1, where here L is the degree or order of m of s of a. Okay, the minimal polynomial of a. And remember, I have defined this as nothing but p of a. Okay, and here p of s is called the interpolating polynomial. Okay, so that was the equation that I used in order to be able to find this f of a. So remember, in order to be able to find f of a, we were finding these unknown coefficients, and these are coming from the interpolating equations. And the interpolating equations are in this form. So I have lambda j and equals to p P of lambda j. And here I take the third order derivative of these polynomials. And here j changes from 1 to k, the distinct eigenvalues of A. And here t changes from 0 into mj minus 1. Okay? The power of the eigenvalue lambda j in the minimal polynomial. Okay, so this was the theory that we have seen. Now we're going to, this was the first method of calculation of f of a. Now we're going to see the second method for calculating f of a. So I have second method for calculating f of a. And the second method is going to use the following representation. We know that we can write the Jordan canonical form of the matrix A as P inverse AP. Okay? So we have learned so far for an arbitrary matrix how to find this Jordan canonical form and how to find a P matrix that would satisfy this equation. So given A, I know J and P. Okay? And the second method of calculation of f of a is based on this simple equation. Okay? So now we're going to look at this equation first. So this is called a similarity transformation of A. So if you define a matrix B which is equal to P inverse AP, then B is called a similarity transformation. Sorry. This operation that defines B, which is this P inverse AP. This operation here, a similarity transformation. Okay? And if two matrices are related to each other with a similarity transformation like this, then we call those two matrices similar matrices. So here A and B are similar matrices. Here P can be an arbitrary invertible matrix, so, and B doesn't really have to be in Jordan canonical form here. And as soon as we see such an operation in linear algebra, we think that we apply a similarity transformation to A by multiplying it with P inverse from the left and by multiplying it with P from the right, then B becomes similar to A. And as soon as you see a similarity transformation, there is a very, very well-known property in linear algebra, and that is that the eigenvalues of similar matrices are the same. Okay? So here, even if B is not in Jordan canonical form, the eigenvalues of A and B would be the same, whatever P is, as long as it is invertible. Okay? So any similar matrices, any two matrices AB which are related with the same equation here, they would have the same eigenvalues. Of course, they can have different eigenvectors, but their eigenvalues are preserved under similarity transformation. Okay? So here, if we come back to this equation, we see that we have A and J. A and its Jordan canonical form are similar matrices. That is actually why the eigenvalues of A is also, they are also the eigenvalues of the Jordan canonical form. Okay? So here we have learned so far how to calculate Jordan canonical form and A. That means that I can write A in terms of the Jordan canonical form of it and the matrix P. So if I extract A from this equation, I get Pj P inverse. Okay? So this is a decomposition of the matrix A. And if J is diagonal, so if I have a diagonal Jordan canonical form, then this would be an eigen decomposition of A. Okay? So this P, J, and P inverse would become an eigen decomposition of A, the matrix A. Okay? So usually people write in such a case, if J is diagonal, people would write it like this, where the matrix lambda, this is capital lambda, the matrix lambda is a diagonal matrix where the eigenvalues are on the main diagonal. Okay? But of course we know that the Jordan canonical form does not have to be a diagonal matrix in general. That means that this is not applicable in the most general case. But this is a decomposition of A into its Jordan form and into the P matrix. So this is called a Jordan decomposition of A. Okay? Jordan decomposition of A. And the second method of calculating f of A is based on this Jordan decomposition. If given A, if I can calculate P and J, then I can use those two matrices in calculating the function of the matrix A. Okay? So here let us look at this f of A. So f of A is given by that formula, I from 0 to infinity, I have alpha I, A to the I. And now I use this decomposition in this formula. So I from 0 to infinity, alpha I, and Pj times P inverse to the power I. Okay? So you see that here I need to calculate the power of this Jordan decomposition. Okay? We are going to see that this Jordan decomposition behaves very well under this power operation. So we would see that I can take this power operation from outside this Jordan decomposition into on top of the J matrix here. Okay? So now let us see how I can do that. So Pj P inverse. What is the zeroth power of Pj P inverse? I equals to 0 is the first term here. I know that zeroth power of any matrix is the identity matrix. Okay? Then let us look at the first power. Pj P inverse to the power 1 is Pj P inverse, of course, to reveal. And what about Pj P inverse square? In this case, I need to multiply this matrix with itself. So I have Pj P inverse, this is the matrix, times itself, Pj P inverse. Okay? Here, P inverse P is the identity matrix, so it can disappear from this multiplication. And J times J is J square, so I have as the result P times J square times P inverse. Okay? So you see here that I can take the square directly inside onto the matrix J. Okay? So really I don't have to take the square of P or square of P inverse here. I can take the square directly here onto J. Okay? What about cube? So Pj P inverse cube is Pj P inverse square, Pj P inverse square times Pj P inverse. Okay? So here Pj P inverse square is this matrix. So I have Pj square P inverse times Pj P inverse. Okay? And this is again identity, and I would have J squared times J, which is J cube, P times J cube times P inverse. Okay? So we see here that we can actually generalize this property here. So the cubic power can also be taken on top of J here. So I can actually write the general property here, Pj P inverse times the identity to the power I, Pj P inverse to the power I, is nothing but P times J to the power I times P inverse. Okay? So this is our property that we're going to use. So I'm going to now substitute that power expression into my summation here, into f of A. All right? So now let us do that. So I can write f of A here. f of A is I from 0 to infinity. Here, instead of this pj p inverse I will substitute this expansion here. So I have alpha I pj to the I p inverse. Okay? So you see that in the summation there are some terms which are not related to I. So this p is not related to I and p inverse is not related to I. That means that I can take p parenthesis from the left and I can take p inverse parenthesis from the right. So this is going to give me, in p parenthesis, I have I from 0 to infinity, alpha I, j to the I, and I have p inverse here. So now this formula is quite important because in this case I see that there is a matrix in the middle which is related to only the Jordan canonical form of the matrix A. Okay? So what can you say about this matrix? Summation I from 0 to infinity alpha I j to the I. So this is exactly the function of the matrix J. Remember, f of s is nothing but I from 0 to infinity alpha I s to the I. And if I substitute instead of s the Jordan canonical form, then I would obtain this matrix. So instead of A, I have here J. That means that this is f of J itself. Okay? So that means that I have here P times f of J times P inverse. Okay? So here you see the following equation then. F of A is nothing but P times f of J times P inverse. So we see something very important here. Given A, I can calculate P and J matrices. And then, instead of taking the function of the actual matrix A, I can take the function of its Jordan canonical form, the same function of its Jordan canonical form, and then I would put it here in the middle and multiply it with P and P inverse from the left and from the right. Then I would obtain the f of A that I would like to calculate. In general, the matrix A can be filled with non-zero elements, but we know that the Jordan canonical form would be filled with as many zeros as possible. So this matrix J is much simpler than the actual matrix A in many cases. Okay? That means that calculating f of J might be much more easier than calculating the function f of A. Okay? So when we get a matrix A, therefore what we can do is to calculate J and P and then take the same function of the Jordan canonical form and use this formula to calculate f of A. So here, this is an indirect way of calculating the function of a matrix using its Jordan canonical form. So in order to be able to calculate the function of a matrix, all I have to do is to know the J and P and then calculate the function of its Jordan canonical form. And then this formula is going to give us the function of the original matrix A. Okay? So that is very good. So now we are going to be looking at how we can calculate f of J. So I have the matrix J looks like this. I have some number of Jordan blocks here. Some of them might belong to the same eigenvalue. So I have some Jordan blocks in the Jordan canonical form. Okay? And Jordan canonical form is block diagonal, so it's formed out of some blocks. And we know that these blocks are called Jordan blocks. And some of them can belong to the same eigenvalue or distinct eigenvalue. Here I number each of these blocks. And each of these blocks would be in the following form. So JT, the tth block here is in the following form. I have lambda j. I would have eigenvalues on the main diagonal. And I would have ones above the main diagonal. And I would have such a matrix. So each Jordan canonical form is formed out of these simple Jordan blocks. Okay? Now we would like to calculate the function of this matrix, f of J. Okay? So that we can substitute it here into this formula to calculate our final aim here, which is f of A. Okay? So now let me try to write f of J here. F of J is I from 0 to infinity, I would have here alpha I, j to the I. Okay? If you take the power of a block diagonal matrix, then it is sufficient for you to take the power of each of its blocks. Okay? So if you take the power of a block diagonal matrix, you can take the power of each of its blocks and you are done. Okay? So I have this is equal to I from 0 to infinity alpha I, and j to the I is going to be in the following form: j1 to the I, j2 to the I, going until j sigma to the I. Sigma is the total number of Jordan blocks in the Jordan canonical form. Okay? So then this is a block diagonal matrix again, and I have the scalar multiplication here, and I have the summation. Now I'm going to take the scalar multiplication inside the matrix, and then I will take the summation inside the matrix as well. Okay? So I would have I from 0 to infinity, alpha I, j1 to the I. And I have I from 0 to infinity, alpha I, j2 to the power I. And I would have at the end I from 0 to infinity alpha I, j sigma to the power I. These are also blocks. This is also a block diagonal matrix, and you see that I would have these summations as instead of the blocks here. Okay? So then what is this matrix, or what is this matrix? So these are again in the summation 0 to infinity alpha I s to the I substituted j1, and then I substituted j2, etc. Okay? So these are again functions of the matrices, or functions of these Jordan blocks. All right? So Jordan canonical form is formed out of Jordan blocks. So the function of the Jordan canonical form is formed out of the functions of each Jordan block in the Jordan canonical form. Okay? So here I can write here f of j is nothing but, this is f of j1. This is f of j1. F of j2 going until f of j sigma. Okay? So function of the Jordan canonical form is nothing but is composed of the functions of each of its sub-blocks, okay? Each of its Jordan blocks. So if I can find the function of each of such Jordan blocks here, I can find the function of the overall Jordan canonical form, okay? So here this means that we can divide the problem into some sub-partitions, and in each partition I can calculate the function of a single Jordan block, and then I combine the functions of each of these blocks to obtain the function of the Jordan canonical form, and then I can substitute it back into this formula, and then I can find the P, I can multiply the result with P and P inverse from the left and from the right, and I obtain the function of the overall A matrix. Okay? So it is sufficient for us to be able to calculate only function of a single Jordan block, because function of this Jordan canonical form can be formed out of the functions of each of these Jordan blocks. So if I know how to calculate the function of a single block like this, then I can form all of the other matrices here. Okay? So now we're going to concentrate on how to find the function of a single Jordan block given here. So in this case, I'm going to take a single Jordan block. So we're going to find f of jt, okay? Function of a single Jordan block, all right? So here I have jt equals to, I would have that matrix, lambda j, going until here, and I would have ones, and I would have zeros. So let us say that this Jordan block has the size dt by dt. Okay? The size of the t Jordan block is dt by dt. Okay? Now we're going to calculate function of this single Jordan block, and we'll look at what the final form of it is. So now I'm going to be using this. So f of s is I from 0 to infinity alpha I s to the I. So in general, if lambda j is not actually 0, then you can see that when you take the powers of this matrix JT. If I use this expansion here, then I am going to get f of JT as follows: I from 0 to infinity alpha I and JT to the power I. So in general, powers of JT, powers of this matrix, if alpha j, the eigenvalue of the Jordan block, is not equal to 0, the powers of this JT would be all non-zero. Okay? So all of these powers would be non-zero, so I would have infinitely many terms here in this summation. Then I need to actually write this summation as a finite summation here by replacing any power of JT with powers larger than or equal to L or higher, in terms of as a linear combination of its lower powers using the Cayley-Hamilton theorem, or its version for the minimal polynomial. Then I need to write this as a finite polynomial here, and then I need to find the unknown coefficients. So I need to write this as C0 identity, C1 JT, going until CL minus 1 JT to the L minus 1, and then I need to find these coefficients because there are infinitely many terms here. But here, fortunately, there is an easier way. So here, in this method, I need to use the first method of calculation that we have seen in the last lecture. But here, I don't want to apply it here. So instead of this approach, we're going to use another Taylor series expansion. This was the Taylor series expansion around S0 equals to 0. So remember the general form. F of s is equal to I from 0 to infinity. I would have f to the ith order derivative S0 over I factorial times s minus S0 to the power I. Okay? So here, there is actually a very good candidate for this S0. Okay? So there is a cat here. Maybe I should shut her down, sorry. Okay, I'm back. I have taken it outside, sorry for this. So here, this is the Taylor series expansion in the general form. Here, there is a very good candidate for this operating point S0, all right? So you see that the eigenvalue of this block here, and that is what I'm going to do here. I will choose S0 equals to lambda j, the eigenvalue of the Jordan block. In that case, we will see that things are going to be really very simplified. So here, let me substitute this S0 equals to lambda j. F of s is equal to I from 0 to infinity fi of lambda j divided by I factorial times s minus lambda j to the power I. Okay? So now I can actually use this expansion in my function of JT calculation. Okay? Then f of JT would be I from 0 to infinity fi evaluated at lambda j divided by I factorial times JT minus lambda j times identity to the power I. Okay? So here, if I substitute s equals to JT, then I would obtain this expansion. Okay, so this is going to be our expansion that we are going to use to calculate the function of a single Jordan block. Okay, so this is going to be much more useful than the actual expansion here at S0 equals to 0, because we are going to see that the powers of this matrix JT minus lambda J identity, only a finite number of them will be non-zero. Okay, so now let us look at that matrix. JT minus lambda J identity would be just this. I would have zeros below the main diagonal, and I would have zeros on the main diagonal, because I'm subtracting lambda J from the main diagonal here by subtracting lambda J identity from this matrix. And I would have ones above the main diagonal, and I would have zeros everywhere else. Okay? And as soon as you do that subtraction, you see why this matrix is quite simple to deal with. Okay, so here, this is really a simple matrix, and the type of this matrix is called in linear algebra literature as the nilpotent matrix. So its some powers are going to be 0 exactly. Okay, so remember, when we try to obtain the dimensions of the null spaces of Jordan, a matrix in Jordan canonical form, we have encountered this type of matrices. Okay, and we have seen that when I take the increasing powers of this matrix, then I would get at the end a 0 matrix. Okay, so the powers of this matrix larger than or equal to some specific power will be exactly equal to 0. So there will be only finite number of terms in this infinite summation, because this JT minus lambda J identity to the power I will be exactly equal to 0 when I increases above some value. All right? So here I would have, now we can look at the powers of this matrix. JT minus lambda J identity to the power 0. What do you think this matrix is? 0th power of any matrix would be just identity matrix. So I would have ones here and zeros everywhere else. This is the identity matrix. Now JT minus lambda J identity, the matrix itself is given this one, 0, zeros here, ones above the main diagonal, and I would have zeros. Okay? So now let us look at JT minus lambda J identity. JT minus lambda J identity square. Try to take the square of this matrix. You would see that these ones here, only non-zero elements of this matrix, would travel one row up or one column up, okay, or one diagonal up, and then you will get the following matrix. I would have zeros on the main diagonal, and I would have zeros in the first super diagonal here. This is called the first super diagonal of the matrix, and these elements are called sub-diagonal elements, and these elements are called super-diagonal elements. So I have the first super-diagonal, second super-diagonal, third super-diagonal, etc. So this matrix has zeros on its main diagonal, and it has ones in its first super-diagonal, and it would have zeros in its second super-diagonal, and so on. Okay? But here, when I take the square of this matrix, I know that these ones are going to travel one diagonal up. So there will be ones here, okay, in the second super diagonal, and I would have zeros everywhere else. Okay? So then if I continue in this manner, if I take the cubic power, then you know that these ones will travel even to higher diagonals. Okay, so I would have JT minus lambda J identity cube is going to have the following structure: zeros on the main diagonal, zeros on the first super diagonal, and I would have zeros in the second super diagonal, and I would have ones in the third super diagonal, and I would have zeros. Okay? Everywhere else. So I know that at some power, these ones are going to travel to this corner. Okay? At some power, these ones are going to reach to this corner. And what is that power? Jt minus lambda j identity to some power is going to be looking like this. There will be only one here, okay? And there will be zeros everywhere else, okay? So some power of this matrix is going to be this matrix, okay? So which power do you think it is? Which power do you think it is? Okay. So here, let me look at it here. The matrix is dt by dt. Okay, and so therefore there are dt elements in the first row. There are dt elements in the first row. And when I take the first power, this one is at the second element of this row. In the second power, this one is in the third element of this row. And in power 3, this one is in the fourth element of this row. At which power is this one in the last element of this row? So the last element is dt element, so it is going to be one less here. The power is going to be dt minus 1. Okay? So the dt minus first power of this matrix would be just this matrix. What is going to happen when I increase the power even more? What is going to be the dtth power of this matrix? You know that then even this one is going to disappear from this matrix, and the matrix is going to be 0. So here I see that this jt minus lambda j identity to the power d is going to be a completely 0 matrix. Okay? So it is 0 dt by dt. And if this d is larger than or equal to dt. Okay? So if I take any power of this matrix which is larger than or equal to the size of this matrix, dt, then the power is going to turn out to be equal to 0. Okay? So this is very good, because in this summation there are infinitely many terms. And that means that I really do not have to sum infinitely many terms here, because for I is larger than or equal to dt, these terms would be equal to 0. That means that I need to sum here only the I values from 0 to dt minus 1. Okay? So that is the advantage of using S0 equals to lambda j here. All right? If I use S0 equals to 0 for this block, then all of the powers would be non-zero here, and I would have to use the first method of calculation to calculate the f of jt. Okay? So now let us actually use these results to obtain f of jt. Oh, sorry, I have erased the parts that I shouldn't erase. So you know that any power which is higher than or equal to dt would be 0. Okay? So now let us write f of jt. F of jt is going to be formed, so maybe I should first write the finite summation here. I know that f of jt is that thing, so I have this summation, but I know that if I is larger than or equal to dt, these terms would be 0. So I can write here only the finite summation, I from 0 to dt minus 1. Okay? So I have f of I, fi order derivative evaluated at lambda j divided by I factorial and jt minus lambda j identity. Okay? And I have to the power I here. So here I am going to multiply I equals to 0 matrix with a scalar plus multiply this with a scalar plus multiply this with a scalar plus sum all of these matrices by multiplying them with scalars. All right? So now I'm actually ready to write f of jt. So it is going to be a large matrix. I will write it like this. I need a large space. So here, let me look at these matrices. All of these matrices are upper triangular. Okay? An identity matrix is both upper triangular and lower triangular. So it's upper triangular, upper triangular, upper triangular. All of these matrices are upper triangular, these many matrices. That means that this f of jt would be upper triangular as well. So it is elements below the main diagonal would be equal to 0. Okay? What about the main diagonal? In the main diagonal is going to be determined by these matrices. But which matrices here can contribute to the main diagonal? This zeroth power is non-zero on the main diagonal, and the first power is 0 on the main diagonal, second power is 0 on the main diagonal, third power is 0, and dt minus first power is 0 on the main diagonal. Okay? So only the zeroth power can contribute to the main diagonal. Okay? So what does that mean? Only I equals to 0 term will contribute to the main diagonal of this matrix. Okay? So, and what is going to be that term? If I equals to 0, I would have f to the 0th order derivative, but it means that no derivative is here. F of lambda j divided by 0 factorial, which is 1. Okay? So I would have f of lambda j times jt minus lambda j identity to the power 0. Okay? This is the 0th term. And it is only this term that is going to contribute to the main diagonal. Why is that? Because all of the higher powered matrices would be 0 on the main diagonal. Okay? So that means that I am going to multiply the identity matrix with the scalar f of lambda j, and then these are going to form my main diagonal elements. Okay? So I would have f of lambda j here. What about the first super diagonal? So these are the main diagonal elements. What about the first super diagonal? The elements above the main diagonal. Okay? They are going to be determined by which I values. So I see here that the 0th power is 0. Its first super diagonal is 0. The first power has ones on its first super diagonal. So you see that this matrix is going to be able to determine, or is going to be contributing to those first super diagonal elements. This matrix has 0 first super diagonal, 0 first super diagonal, and 0 first super diagonal. So we see that only the power I equals to 1 is going to determine the first super diagonal of this matrix. Okay? So only this matrix is going to determine. And we see that what is the constant multiplier here, constant coefficient when I is equal to 1. When I is equal to 1, I would have f to the first order derivative evaluated at lambda j divided by 1 factorial, but it is still 1, okay, times jt minus lambda j identity to the power 1. Okay? And all of the other I values will not change the first super diagonal. Okay? So that means that I'm going to multiply this matrix with the scalar f prime of lambda j. So I have f1 of lambda j, f1 of lambda j here, and here f1 of lambda j in the first superdiagonal of f of jt. Okay? And what about the second superdiagonal? In the second superdiagonal, I would have these elements, I would determine these elements, and which matrix is going to be contributing, or which power, which I values would be contributing to the second superdiagonal. I see that only this matrix is not, has a non-zero superdiagonal, second superdiagonal here. That means that it is only I equals to 2 which is going to determine this second superdiagonal of this matrix. All right? And what is the coefficient for the second superdiagonal? I would have f to the second order derivative lambda j divided by 2 factorial, okay? And I would have here f second order derivative lambda j divided by 2 factorial, and these are going to continue here, okay? And these are going to continue in this manner. So I would add the elements which are the ith order derivatives evaluated at lambda j divided by I factorial. What is going then what is going to be, so these are going to increase like this, and we are going to come to the corner element here, top right element, okay? In that case, it is only the dt minus first power which is going to determine that corner element. Okay? So the element here is going to be determined by substituting I equals to dt minus 1. So I would have here f to the dt minus first order derivative evaluated at lambda j divided by dt minus 1 factorial. Okay? And then this is going to complete. It is not looking very good, right? Sorry, it really looks terrible. So let me write it as follows. So I have f to the, maybe a little lower, f to the dt minus first order derivative evaluated at lambda j over dt minus 1 factorial. Okay? So I would have this element. So this actually completes our theory of the function of this single Jordan block. Okay? So this is a dt by dt matrix again. Okay? And here I can actually look at what happens if dt is 1. If dt is 1, then I'm going to take this part of this matrix. Okay? So let me actually draw this a little bit like this. If dt is 1, I will take only these parts. So if I have a 1 by 1 block, then I would use only this 1 by 1 part of this matrix. If dt is 2, then I would use these parts. If dt is 3, then I would use this 3 by 3 part of this result. Okay? And if dt is arbitrary, then I know what the overall matrix should be. So any function of a single Jordan block can be written in this form. Okay? All you have to do is take the derivatives of f and evaluate them at the eigenvalue of the Jordan block, which is lambda j. Depending on the size of the Jordan block, you can use the increasing sized elements of such a matrix. Okay? So when you apply this theory to all Jordan blocks in your Jordan canonical form, you are going to get the function of the Jordan canonical form. And then you will multiply it with P and P inverse from the left and from the right, and then you will get the function of the overall matrix. Sorry. So now we're ready for some examples. example. So this is a very, very simple example of a matrix that we have seen before. And here we have to calculate e to the a and log a using the second method that we have learned now. So here we have already calculated this e to the a and logarithm of a using the first method of calculation, and then now we're going to apply the second theory that we have learned onto the same task. So here I know that in this case the eigenvalues of this matrix are 3 and 1, and the eigenvectors are 1, 1 and 1 minus 1. Okay? So then if I would like, so this is a Hermitian matrix, and that means that I can form my P matrix out of the eigenvectors 1, 1 and 1 minus 1. And the Jordan canonical form would be diagonal, composed of the eigenvalues. Okay? So now I can actually write this A matrix as P times J times P inverse. This is my P matrix, and the Jordan canonical form is just this, P times, and J is this, 3, 1, 0, and P inverse. Okay? So now we see that this is my Jordan canonical form, and I need to take its function. We know that f of a is P times f of j times P inverse. So I see that in this case the Jordan canonical form is formed out of two Jordan blocks with sizes 1 and 1. Okay? So I have two Jordan blocks here. This is my first Jordan block whose size is 1 by 1, and this is the second Jordan block whose size is 1 by 1. Okay? So now what I have to do is, when I try to calculate f of a, then that is going to be P times f of j times P inverse. And I know that f of j can be obtained by passing these single Jordan blocks out of the function f. And this is going to be P f of 3, f of 1, and I would have 0, okay, times P inverse. So we see here that when the blocks are 1 by 1, then this means that you have just scalars, okay? So you would only use this part of this overall dt by dt matrix. If dt is 1, then you would have only this, which means that you need to pass the eigenvalues out of the function, pass the eigenvalues through the function f. And here we reach that thing. So we pass the eigenvalue 3 from the function f, we pass the eigenvalue 1 from the function f, and then we obtain the Jordan function of this Jordan canonical form. And then we multiply it with p and p inverse, then we are done. Okay? So now let us try to apply this theory. So e to the a is going to be, then f is, then what is f in that case? In that case, f is e to the s. Okay, f of s is e to the s. That means that here I need to substitute s equals to 3 and s equals to 1. So this is p times e to the 3, and I have e to the 1, which is e, and I would have just this, p inverse. So if you write this matrix P here, and if you take the inverse and put it here, if you do the multiplication, you're going to calculate e to the a. Okay? And what about the logarithm of a? It is not more difficult. So I have logarithm of a is P. Now instead of e to the s, I will pass these eigenvalues from the logarithm function. Log 3 and log 1, which is 0. So I would have this one. Okay? So now we're going to pay some special attention to the structures of these matrices. So you see that A is written Pj P inverse, and here J is a diagonal matrix because we have a Hermitian matrix in this case. Okay, so Pj P inverse. So this is an eigen decomposition of the matrix A. Okay, So this is an eigen decomposition of the matrix A. The eigenvectors are going to be the elements of columns of P, and the eigenvalues would be on the main diagonal of the matrix lambda or J, as we call it in this case. Okay? So this is an eigen decomposition of the matrix A. But look at F of A. F of A just has the same structure as A. Okay? So F of A has exactly the same structure of A, except for that these diagonal elements are changing. Okay? So the eigenvalues of A are on the main diagonal of its Jordan canonical form. What about the eigenvalues of the function of the matrix F of A? What can you say by looking at this type of decomposition? What can you say about the eigenvalues of the matrix F of A? So you see that this is nothing but the eigen decomposition of F of A. Okay? So I have the eigenvector matrix, I have the eigenvalues on the main diagonal of the matrix here, and I would have P inverse. So this is nothing but the eigen decomposition of the matrix F of A. That means that the eigenvalues of F of A are nothing but F of 3 and F of 1. Okay? Eigenvalues of e to the A is e cubed and e. Eigenvalues of logarithm of A is log 3 and 0. Okay? So you see here, when you know the eigenvalues of the matrix A, you directly know the eigenvalues of the matrix F of A. And how do you obtain them? You obtain them by passing the eigenvalues of the matrix A from the function F. Okay? So here e cubed and e are nothing but the function nothing but what we get when we pass 3 and 1 from the function e to the s. Okay? And vice versa, and so on here. So here this is not, we are going to see that such a fact is not dependent on whether the Jordan canonical form is diagonal or not. Even when the Jordan canonical form is not diagonal, we are going to see that eigenvalues of the matrix F of A would be always F of lambda j, okay, where lambda j's are the eigenvalues of A. Okay, so it is always going to be the case that the eigenvalues of the matrix F of A would be the eigenvalues of A passing through the function F. Okay, so here I will write this as a remark. Eigenvalues of F of A are F of lambda I, where lambda i's are the eigenvalues of A. Here, this fact will not be dependent on whether the Jordan canonical form is diagonal or not. Here in this example, the Jordan canonical form was diagonal. But even when the Jordan canonical form is not diagonal, when it is upper triangular, then we are going to see that the eigenvalues of the matrix F of A would always be the eigenvalues of A, the matrix itself, passing through the function F. Well, this completes this example. Now let us look at a second example. So the second example is going to be a matrix in Jordan canonical form. So I would have A equals to, I would have 1 over 2, 1 over 2, 1 over 2, and 1, 1 here, 0, 0, 0. A 3 by 3 Jordan block, 3 over 2, 3 over 2, and I would have 1, a 2 by 2 Jordan block. Of course, the eigenvalues sometimes might be the same. Here I have taken the distinct eigenvalues are different for different Jordan blocks. So I have 5 over 2 here, a 1 by 1 Jordan block. Okay, so this is my A, And the task is to calculate sine pi a. Okay, this is the question mark. So we would like to calculate this function. So now let me erase some more parts there. So now this is a matrix in Jordan canonical form. Okay? But if you suppose that you don't know this second method, suppose that you would like to use the first method of calculation here, then what would you do? You would calculate the characteristic polynomial, and that is going to be s minus 1 over 2 cube, s minus 3 over 2 square, and s minus 5 over 2. Okay? This is the characteristic polynomial. What is the minimal polynomial? M of s would be s minus 1 over 2, s minus 3 over 2, s minus 5 over 2. What about the powers here? This power is going to be the size of the largest Jordan block for eigenvalue 1 over 2. The size of the largest Jordan block for the eigenvalue 1 over 2 is 3. Okay? And the size of the largest Jordan block for eigenvalue 3 over 2 would be 2 by 2 block here, and this size would be 1. Okay? So this is my minimal polynomial. What is the order of the minimal polynomial? It is going to be L equals to, the order of the minimal polynomial is the summation of these powers. So here in this case, minimal polynomial is equal to the characteristic polynomial, because for each eigenvalue I have only a single Jordan block. Okay? So now L equals to 6, and that means that if I would like to calculate this interpolating polynomial, what is going to be its order? Its order is going to be 1 less than the minimal polynomial order. So I would have C0 plus C1s, C2s squared, C3s cubed, plus C4s to the 4, plus C5s to the 5. Okay? It's a fifth order polynomial, and how many unknowns do we have? We have just 6 unknowns in this case. So we're going to have to write 6 equations in terms of these C0, Ci parameters, and then we have to solve for them for each of these parameters. Okay? And then I need to write P of A as C0 identity, C1a, C2a squared, C3a cubed plus C4a to the 4 plus C5a to the 5. So I need to take some powers of that matrix, and I need to take until the 5th power, and then would weight them with these coefficients and then sum everything. Okay? So here you see how cumbersome that method looks here. Okay? On the other hand, the matrix is just, so here we will not use this method at all in this case. The matrix is already in Jordan canonical form. So I'm going to use here A equals to Pj P inverse. Okay? The second method of calculation. And what is P in this case? How can you find P? You can actually try to apply our theory here, but do you really need to? In this case, do you really need to look at those null spaces? The matrix is already in Jordan canonical form. That means that the matrix A is equal to J. Okay? That means that P here is nothing but the identity matrix. If you use our procedure for calculating the P matrix, you can find the same P matrix. Okay? So here I would have A is equal to J. Okay? And in this case you see here that A is composed of 3 Jordan blocks. A is composed of J1, J2, and J3. Okay? And I would have zeros everywhere else. J1 is this one, J2 is this block, and J3 is this scalar. Okay? So I can actually write here f of A is equal to f of J1, f of J2, and f of J3. And I would have zeros everywhere else. Okay? Now I'm going to take each block here and then I will calculate the function of that block. Okay? So here J1 is this block. J1 is, I have 1 over 2's here and 1's above the main diagonal and I would have zeros. Here, what is f of s? F of s in this case is sine pi s. Okay? That is where I would like to substitute s equals to a. And then I will calculate sine pi j1. Okay, what is this going to be? In order to be able to calculate this, I'm going to use my theory. Now J1 is a 3 by 3 Jordan block, so I will use only the 3 by 3 part of this theory. Okay? So on the main diagonal, so what is lambda j for J1? For J1, lambda j is 1 over 2. Okay? The eigenvalue is 1 over 2. And you see that to be able to use the 3 by 3 part of this theory, I would need f prime, and f double prime. What is f prime of s here? This is going to be pi cosine pi s. Okay? And what about f double prime of s? It is going to be the derivative once more with respect to s, and it's going to be minus pi square cosine pi s. Okay? So I would have this one. So now let us use this theory, use that theory. Below the main diagonal, I would have zeros. So these three elements would be 0. On the main diagonal, I need to pass the eigenvalue of the Jordan block from the function. Eigenvalue of the Jordan block is 1 over 2. I need to pass 1 over 2 from this function. Sine pi times 1 over 2 is sine pi over 2, which is 1. Okay? So on the main diagonal, I have 1. And on the first super diagonal, I have f prime evaluated at the eigenvalue of the Jordan block. F prime is this one. Evaluate this at 1 over 2. So pi cosine pi over 2. Cosine pi over 2 is 0. That means that the super diagonal is 0. Now the final thing is this element. It is the second derivative of f. Evaluate it at the eigenvalue of the Jordan block. Second derivative of f is this one. Evaluate this at the eigenvalue of the Jordan block, which is going to be, sorry, this derivative is wrong, right? So I have pi cosine pi s, and if I take its derivative, it's going to be minus sine. So I would have minus pi square sine pi s. Evaluate this second derivative at s equals to pi over 2. Sorry, 1 over 2. Then I would have sine pi over 2, which is 1. So this is going to be minus pi square. Do you think this is right? So you see here, when you look at this matrix, never forget here, this was f of lambda j divided by 0 factorial, which was 1. This was divided by 1 factorial, which was 1. So there is always an I factorial here in this formula. So here, I need to write, this is the second derivative. That means that I need to divide it with 2 factorial, which is 2. Okay? So this is going to be pi square over 2. Okay? This is the sine pi of the first Jordan block. All right? So now let us look at J2. In this case, J2 is 3 over 2, 3 over 2, 1, 0. And sine pi J2. In this case, I would use only the 2 by 2 part of this theory here. Below the main diagonal, I have zeros. The matrix should be upper triangular. And I would have on the main diagonal, I need to pass the eigenvalue of the Jordan block, which is 3 over 2 from the function f. Sine pi 3 over 2. Sine 3 pi over 2 is minus 1 on the main diagonal. And 1 above the main diagonal, or the first super diagonal, is going to be past the derivative of the function, past the eigenvalue from the derivative of the function. So I have 3 over 2, cosine 3 pi over 2 is still 0, so I would have 0 here. So you see that, and I have a non-diagonal matrix, but when it passes from the function, I get a diagonal matrix, which is fascinating. So finally, I have the third Jordan block, J3, which is equal to the scalar 5/2. It's a 1-by-1 matrix, okay? So sine pi J3 is going to be just sine pi 5/2 past this. So a 1-by-1 scalar, a scalar is a 1-by-1 matrix. What is it? Is its eigenvalue itself. Okay, so 5/2 is a 1-by-1 matrix, 1-by-1 Jordan block with eigenvalue 5/2. Okay, so I will use only the 1-by-1 part of this theory. So that means that sine pi 5/2 is going to be just 1. Okay. This is a 1-by-1 matrix. So that means that I can actually write the overall sine pi A just like this. Okay? Sine pi A is just, now I would have 1, 1, 1, 0, 0 here. And I would have minus pi square over 2, and I would have minus 1, 0, 0 here. These are my blocks. And I would have just the block 1, 1-by-1 block. Okay? So this is my final answer. So you see that solving this question by using the first method would be really a torture. Okay? So in that case, you need to find 6 coefficients by solving 6 equations. And none of the eigenvalues, some of the coefficients might turn out to be 0, but at the end, if C5 or C4 turns out to be non-zero, then you need to calculate the 4th power of such a matrix, or 5th power of such a matrix. Okay? And now let me look at the eigenvalues of the matrix sine pi A. The eigenvalues, this is an upper triangular matrix. The matrix is not diagonal, it's upper triangular. And what about the eigenvalues of sine pi A? They are these elements, 1, 1, 1, minus 1, minus 1, and 1. What about the eigenvalues of A? Eigenvalues of A are 1/2, 1/2, 1/2. Pass them from that function. Sine pi over 2 are 1. So these 1/2s are transformed into 1s. These 3/2s are transformed into minus 1s, and these 5/2 are transformed into 1 again. So we see here that the eigenvalues of this matrix, they are nothing but f of lambda I, where lambda i's are the eigenvalues of the original matrix A. Okay? So the function sine pi s is, I pass the eigenvalues of this matrix, the original matrix, from the function sine pi s, and then I find the eigenvalues of the function of the matrix. So but here you shouldn't confuse this with the eigenvectors. In general, the eigenvectors of this matrix might be quite different than the eigenvectors of this matrix. If the Jordan canonical form it was diagonal, then the eigenvectors of the matrix f of A would also be the eigenvectors of the original matrix A. But if the matrix A, if the Jordan canonical form of the matrix A is not diagonal, then the eigenvectors of f of A might be quite different than the eigenvectors of the actual matrix A. Okay? So if the Jordan canonical form is diagonal, both eigenvalues are transformed by f, but eigenvectors are preserved. So, but if the Jordan canonical form is not diagonal, then the eigenvalues are transformed with f again, but the eigenvectors might not be preserved. They might be different than the eigenvectors of A. Okay? So the final function of a matrix topic that we are going to see is going to be the square root function. So we're going to now try to take the square root of a matrix. And we're going to use our standard example in that case, the favorite matrix 2, 1, 1, 2. Okay? So example, this is the last example, by the way. So I have the square root of a matrix. So in this case, I'm of course considering f of s is equal to s to the 1 over 2, or square root of s. Okay? In general, the square root of a matrix is defined as follows. A to the 1 over 2 is defined as the matrix, as a matrix, let us say. You will see why I say A instead of D. So A1 over 2 is defined as a matrix, A to the 1 over 2, which satisfies the following equation. A1 over 2 times A1 over 2 is equal to A. Okay? So when trying to find the square root of a matrix, I need to find a matrix that is shown with this notation, a to the power 1 over 2, and this matrix should satisfy this relationship. When I multiply this matrix with itself, I need to get the matrix A. Okay? So now let me try to use this matrix. A equals to 2, 1, 1, 2. This is a Hermitian matrix, of course. Eigenvalues were 3 and 1. Eigenvectors were 1, 1 and 1 minus 1. So that means that the Jordan canonical form is 3, 1. And P matrix is 1, 1 and 1 minus 1. Okay? So now let me try to look at the function of a matrix. This is my F in this case. So these two definitions are different in some respect. We are going to see that this is going to give us a unique result, function of a matrix concept. It is going to give me a unique result. But on the other hand, I can calculate the square root of a matrix in two ways. The first way is to calculate the square root matrix using this definition. Okay? And the second way is to use this definition and try to find a matrix that would satisfy this equation. Okay? So I'm first going to be using this function, and then I will use the function of a matrix concept. So here in this case, f of a, which is a to the power 1 over 2, is going to be, so I know that in this case, the matrix A is nothing but P times 3, 1, 0, 0, P inverse. So what I'm going to do is that I am going to pass these eigenvalues from the function s to the 1 over 2. And then that is going to give me the square root of the matrix. Okay? So this is going to give me P times, so I'll pass 3 from the square root, so I would have square root 3, pass 1 from the square root, it is 1, and this is going to give this matrix, and I would multiply it with P inverse. So in this case, this is going to be my square root matrix. Okay? So I have this matrix. Does this satisfy this equation? So what about the second definition? Do you think it satisfies the second definition? Let me try to check. So I take this matrix and I multiply it with itself. P times square root 3, 1, 0, 0, P inverse. I take this matrix and I will multiply it with itself. P times, I would have square root 3, 1, 0, 0 times P inverse. Okay? I know that these two matrices, when multiplied, will give you identity matrix. So I will just multiply these two diagonal matrices. When I multiply these two diagonal matrices, the result will be just another diagonal matrix whose elements will have these two, the multiplication of the square root 3 with itself, and 1 multiplication of these two numbers. So the multiplication would be p times square root 3 times square root 3, 3, 1 times 1, 1, and I would have 0 times p inverse. But this is the matrix A itself. So you see that the result I found by the function of the matrix definition with this one, then it satisfies the second definition of the square root. Okay? So if you put this P matrix here, and if you put P inverse here, and then if you calculate the multiplication of those matrices, you would find the square root of A. Actually, you would find only a square root of A. Okay? So here, that means that I have also other square roots according to this second definition. Can you find me another matrix, A to the 1 over 2? Which would satisfy the same equation, but which is different than this matrix? Can you find me just another matrix, A to the 1 over 2, which would satisfy this second definition? Think about here. What happens if I make this square root 3 minus square root 3? In that case, all of the computations would be the same, except minus square root 3 will be multiplied by minus square root 3, okay? Which is going to give me 3 again, okay? So you see here that, therefore, I can define another square root as this, according to this definition. This matrix, which is going to be different than the first one, is also going to satisfy this definition, square root definition, okay? So can you find another A to the 1 over 2? Can you find it? Yes, here, instead of taking the minus of square root 3, I can take minus 1 here. So I can put minus 1 here, and when I do these calculations, I will multiply minus 1 with itself, and it would give me again 1. The multiplication would again be equal to A itself. Okay? So another square root, A to the 1 over 2, is P times square root 3 minus 1, 0, 0, P inverse. Okay? And my final question, can you find even another one? Yet another square root. There is actually one in this case. What happens if I make both square root 3 and 1 negative? Okay, at the same time. So a fourth square root, according to the second definition, would be P times minus square root 3 minus 1, 0, 0, P inverse. So we see here that, according to this square root definition, there are actually 4 different square roots of this matrix. Okay? And depending on you take these numbers positive or negative, since we have 2 eigenvalues, 2 non-zero eigenvalues here, depending on whether you take the positive one or the negative one, you would have 2 to the n square roots when you have non-zero eigenvalues of the matrix. Okay? So square root of a matrix using this definition is not really unique. So let me write that. Square root of a matrix A might not be unique. There are cases when all of the eigenvalues are 0, for example. In that case, there would be only 1 square root. So it might be unique or it might not be unique. So in general, it's not unique. Square root of a matrix A might not be unique here. Okay? So in this case, therefore, we have 4 distinct square roots according to this definition. Okay? So here I have, according to the definition, a to the 1 over 2, a to the 1 over 2 is equal to a. Okay? According to the second definition here. But in this case, this function of a matrix that we calculated using the function of a matrix theory, the one that we calculated using our theory, has a very, very specific property. So you see that this matrix A is Hermitian, and its eigenvalues are both positive. Okay? So what can you say about this A matrix? This A matrix is Hermitian, and both of its eigenvalues are positive. That means that this matrix is positive definite. So our A is positive definite in this case. What about these square root matrices? Do you think they are also positive definite? So what you see here on the main diagonals are actually the eigenvalues of these square root matrices. So eigenvalues of this square root matrix is minus square root 3 and minus 1. Do you think this matrix is positive definite? Definitely not, because its eigenvalues are negative. So this matrix is again not positive definite. So this matrix is actually negative definite. This matrix is indefinite because one eigenvalue is positive, the other one is negative. So this matrix is negative definite because both of the eigenvalues are negative. This matrix is indefinite. This matrix is indefinite. So it is only this square root which we use the function of a matrix concept that in its calculation, which is positive definite. Okay? So in general, the square root of a matrix is not unique, but when you try to constrain the square root to be a positive definite matrix, then it is going to be unique. So this is called the unique positive definite square root of the matrix. Square root of the matrix. Okay? So in general, the square root of a matrix might not be unique, but we have in general only one positive definite square root. Okay? So, and this positive definite square root would always be unique. Okay? So this is and we find that square root using the function of a matrix concept. Okay? If you go into MATLAB, if you write square root of A with an A matrix, that A matrix, you're going to see that it's going to take the square roots of the elements. So that is element-wise square root, and it's not what we want here. Instead, if you write square root of M, square root M, A, then this is going to give you the positive definite square root of the matrix A. Okay? So it's going to give you only a single answer, and that answer is going to be the positive definite square root of the matrix A. Okay? So I'm at a nice point here. So the course is finished. EE501 is finished with this lecture. So I have completed all of the topics. I would like to again apologize to you that I have spent too much during the lectures, because I couldn't get any feedback during the lecture. So I really do not like this type of lecturing. I really would like to teach in a real classroom. So I hope all of you are actually fine, and I hope that we're going to see each other in the future semesters in real classrooms with better course material. This was all I could do during the pandemic conditions. So I would like to thank you for tolerating me during this period, and I would like to thank you for watching as always. Thank you very much. Bye-bye.